Hello, everybody. We're now going to talk about section 9.2. When last we met, we talked about systems of equations with two variables. Now we're going to step things up a notch and look at systems of equations with three variables. So like before, a good first step in wrapping our heads around how systems of equations work is just understanding at a very basic level, how do you decide if something is a solution? And so here they give us an ordered triple. So the first value there, that's a 3. That's going to be the value of x. The value of y is going to be the next one, -2. And then the value of z is the last number, which is a 1. And when you plug it in, all equations must be true. If only one or two of them work, it is not good enough. Just being true for one or two of the equations is not sufficient. All three of them have to work for all three values. So let's start with the first one, which is x plus y plus z equals 2. We're going to put all three of these numbers into the equation here. 3 plus -2 plus 1 equals 2. 3 plus -2 is 1. And lo and behold, that gives you 2 equals 2. So the first one checks out. That is true. That one works. So what we then need to do is see if the other ones work. So let's try the next equation here. 6x minus 4y plus 5z. If all goes well, that should equal 31. So for x, we're going to replace that with a 3. For y, we're going to replace it with a -2. And for z, we're going to replace it with a 1. 6 times 3 is the number 18. -4 times -2 is +8. 5 times 1 is 5. 18 plus 8 is the number 26. Plus 5 is 31. And lo and behold, that gives you 31 equals 31. So that also checks out. That is a true statement. So we have two of the equations so far are true. So we've got one last equation here. We've got 5x plus 2y plus 2z is equal to 13. We're going to replace the x values. So that's going to be 5 times 3. Then we're going to do the y, 2 times -2, plus 2 times the z, which is 1. And again, if all goes well, this will work out to be 13 and be a true statement. So 5 times 3 is the number 15. 2 times -2 is -4. Here's another +2. That should all equal 13. 15 minus 4 is 11. 11 plus 2 is 13. So that checks out. All three of them were true each time. So the answer is that yes, it's a solution. It does indeed work. It works for all three equations. So we have verified that yes, indeed, 3, -2, 1, that ordered triple is a solution. So that typically is easier to do than to actually solve the system in the first place, which is going to be the main focus of what we're going to be doing next. So what we've got going on here, we've got, we're going to solve this using elimination, which is another name for that addition and multiplication method I was talking about earlier. I was often calling it elimination. So they've numbered off the different equations just to sort of help us tell them apart. And so what I'm going to do first, I'm going to, for step number one, I'm going to eliminate X in two different ways. And I'm just choosing X because it's first. I could do it a different way if I wanted to, but I'm just going to do X because it happens to be in front. So how could I do that? Well, one way I could do that is I could take equation number one and add equation number two. Because the thing to notice is that they already have opposites. I have an X and I have a negative X. That's a good start. That will make it easy to just add them together and get rid of the X's. So I'm going to take equation one plus equation two. That's what this notation means. That's why they've numbered off the equations here for us. So what we're going to do is we're going to take X minus 2y plus 3z equals 9. And we're going to take the other equation, negative X plus 3y minus z equals negative 6. We're going to add all the different matching parts together. As promised, this will eliminate X. X minus X cancels out. Negative 2 plus 3y is going to give me y. 3z minus z, that's plus 2z. And that will equal 9 minus 6, which is 3. And then this equation I'm going to call equation number 4. So I have now gotten a new equation by eliminating X by using the first two. Now I'm going to do that all over again. This time, why don't we do, let's see, if we did 2 times this middle equation, that'll give me a negative 2. That will pair off nicely with the positive 2 that's under it. So what I'm going to do is I'm going to do 2 times equation 2 and then add equation 3. That's what I'm going to do next. So if I do 2 times equation 2, that's going to be 2 times negative X plus 3y minus z equals negative 6. So I'm going to multiply a 2 by each part of the middle equation, the second equation, equation number 2. When I do that, I get negative 2x plus 6y minus 2z equals 2 times negative 6, which is negative 12. The other equation is equation 3, which I'm not doing anything to. That's just going to be 2x minus 5y plus 5z equals 17. And then we're going to do the same thing we did like last time. We're going to add these up, and we are going to eliminate the x's in a different way than last time. 6y minus 5y is just y. Negative 2z plus 5z is going to give me plus 3z. And then negative 12 plus 17 is going to give me the number 5. And then this equation I will name equation 5. So by eliminating x 2 different ways, what I have now accomplished is I have now created a new system of equations with only two equations and two variables. And then once you've done that, then the problem just becomes something like what we were doing in the previous section. Probably the easiest thing to do would be to try to eliminate y. So that'll be the second thing that I'm now going to do. I'm going to eliminate y using equation 4 and equation 5. Maybe I'll write the word and just so it doesn't look like plus. So that is the second step of what we're going to do here. So what I can do is maybe I can do -1 times equation 4 plus equation 5. And if I multiply by -1 here, that'll give me a negative y, and that'll pair off nicely with a positive y. So -1 times equation 4, that's y plus 2z equals 3. You multiply everything by -1, you get negative y minus 2z equals -3. And we're going to take that and combine it with equation 5. And that was y plus 3z equals 5. I'm going to add these equations here. We will end up eliminating the y's because you have a negative y and a plus y. Those will cancel out. -2z plus 3z is going to give you z. -3 plus 5 is going to give you the number 2. And so then we have solved for one of the values, which is z equaling 2. Let me copy this slide here. All right, so now what we're going to do let's see, let's erase some of this stuff. Okay, let's put this equation up there. Okay, and then let's erase a lot of this stuff. Okay, so we have that, and we found that z equals 2. So then what we're going to do for step number 3, we're going to find y using either 4 or 5. I'm going to use equation 4 here that I got earlier. You could just as easily have chosen equation 5. It doesn't make, like I was saying earlier, you have to just commit and follow through with the process. You've got lots of choices to make, different paths you could go down, slight variations on how you could solve any one particular problem. This is the one particular way I'm doing it right now is not like the only way to do it, but you just need to make a choice and follow through on the process here. So for this, I'm going to choose equation 4, and I have a value for z, which is 2. So what I will do is I will say y equals 2 times 2, and that should all equal 3. 2 times 2 is the number 4, so y plus 4 equals 3. subtract 4, and you get y is equal to -1. So now I have 2 of the 3 variables solved. So then in step 4, I'm going to find x using 1, 2, or 3. I have 3 different options. Again, it doesn't make a whole lot of difference which one I happen to choose. You just need to make a decision, pick your favorite equation, and go with it. I'm going to use equation number 1 just because it happens to be first. There's not a compelling reason I have to do it that way. I could just as easily choose something different, and it would all be just fine. You just have to make a choice. So let's see. I know the value of y. That's going to be x minus 2 times y, which is -1, plus 3 times the z. We already found z. That was a 2. And that is all equal to 9. Let's see. -2 times -1 is +2. 3 times 2 is 6. If you add those up, you will get x plus 8 equals 9. Subtract 8. And then when all is said and done, you will obtain x equals 1. So now we have all 3 values, x, y, and z. It's certainly not a bad idea to check your work. You can put the values for x, y, and z into the equations and just check them out. Make sure that this is indeed a solution like we did in the first example. In the interest of time, I'm not necessarily going to take the trouble to do that, but just something to be aware of. You can check your answers, and there shouldn't be any doubt in your mind that your answer is correct. So we write it as an ordered triple. X goes first, followed by y, lastly z. They're just in alphabetical order. So the solution, when all is said and done, is 1, -1, and 2. So that would be how you would approach solving a system with 3 variables and 3 equations. So next, we're going to look at what happens if you end up with an inconsistent system. So what I'm going to do, yet again, what you will notice, here's an x and a -x. Those will pair off nicely with each other. So what I can do is I can do equation 1 plus equation 2. Let's go ahead and do that and see what we obtain. So if I do x minus 3y plus z equals 4, and then we're going to add to that -x plus 2y minus 5z equals 3. We can then add up everything from both equations. The x's get eliminated. -3 plus 2 is going to give me -y. Z minus 5z is minus 4z. And 4 plus 3 is going to give me 7. This equation I will call equation number 4. We'll hang on to that for later. Something else I could do, you notice I have a 5x down here. So maybe if I multiply the middle equation by a 5, that will pair off nicely. That'll give me a -5x to go with a +5x. So what I will do is I will do 5 times equation 2 plus equation 3. Equation 2, we're going to do 5 times equation 2. So that's -x plus 2y minus 5z equals 3. Everything gets multiplied by 5. So that's negative 5x plus 10y minus 25z equals 15. The bottom equation, number 3, that's going to be 5x minus 13y plus 13z equals 8. And then like before, we're going to add everything up. Those will get eliminated. 10 minus 13 is negative 3y. What is this? Negative 25 plus 13, that's going to be negative 12z. And then 15 plus 8 is 23. So this we will call equation number 5. So what I can then do, this is a negative 3y. We would like to have a positive 3y to go with it. So why don't we take negative 3 times equation 4 and then add equation 5. So let's do that. What is negative 3 times equation 4? That's negative y minus 4z equals 7. That's going to give you 3y plus 12z equals negative 21. Meanwhile, this equation 5 is negative 3y, that has a z on it, negative 3y minus 12z equals 23. We will add these up. The y's get eliminated. The z's also get eliminated. I don't know why I keep leaving off the z. So that's going to end up leaving you with 0. And if you do negative 21 plus 23, that gives you the statement 0 is equal to 2. Well, guess what, my friends? That is a false statement, meaning there is no solution. Or the other bit of terminology you can throw around, there's no solution. This is inconsistent, which from what they told us, we kind of sort of knew going in, because they did sort of say this is an inconsistent system. And hey, what do you know? They were right. 0 equals 2. That is not true last time I checked. So lo and behold, that does not have a solution. It is an inconsistent system. Okay. Find the solution to the given system of 3 equations and 3 variables. Notice they tell us from the get-go this one's going to be a dependent system. So let's see. Let's come up with a way to eliminate some stuff, shall we? Let's do, I see I have a 2x and an x. So maybe what I could do is I could do equation number 1 plus a negative 2 times equation 3. So let's do something like that. So negative 2 times equation 3, what's that going to be? It's going to be x minus y plus z equals 0. Everything gets multiplied by negative 2, so negative 2x plus 2y minus 2z, that will equal 0. Equation number 1 is 2x plus y minus 3z equals 0. That will cancel out. We're going to add these up. 2y plus y is 3y. Negative 2 minus, that's not equal. Let's see, negative 2 minus 3 is minus 5z, and 0 plus 0 is 0. So we will call this one equation number 4. What would be another way that we could get rid of the x's? I could do, this is 4 right here, so I could do like just -4 times the bottom one and then add it to equation 2. Why don't we do that? So let's do -4 times equation 3 and then add equation 2. Let's figure out what -4 times equation 3 is. X minus y plus z equals 0. Multiply that all by -4, you get -4x plus 4y minus 4z equals 0. And then we're going to add the middle equation, which is 4x plus 2y minus 6z equals 0. I'm going to add these. Those are going to cancel out. 4y plus 2y is 6y. -4 minus 6 is -10z. And 0 plus 0 is 0. And we will call this equation number 5. So what we then end up with is we have 3y minus 5z equals 0, and we have 6y minus 10z equals 0. So that is equation 4. That is equation 5. If we want to solve for this, what we could do is we could say, okay, what we would need to do, let's multiply the top equation by -2. So we do -2 times equation 4 and then add equation 5. -2 times 3 will give you a -6. That will pair nicely with the +6 that's under it. If we multiply this top equation by -2, I will get -6y plus 10z equals 0. And this is 6y minus 10z equals 0. Lo and behold, when you add those up, both the y and the z cancel out, and you get 0 equals 0. This is a true statement, which is how you know it is dependent. So then what we're going to do is we need to make a statement where we can have something in terms of x and, or something in terms of y and z. So what we can do so we basically just verified that it is indeed dependent. So what you could do, probably the easiest would be to take the third equation. And what you can do is you can solve it for x. Or actually, let's solve it for z. That's kind of customarily what they do. So what you would have is you would have x minus y plus z equals 0. If you subtract x and add y, you can get this equation, which is z equals -x plus y. And then the way that you would write the equation, it's dependent. So it depends on a known value for both x and y. And the way you could write your equation is you could say x, y, and then -x plus y. And so you have everything in terms of x and y, and the value of z is going to be -x plus y. So that is how you could then write your final answer. So that is what it looks like when you have a dependent system with 3 variables. Again, the general overarching strategy, take 2 of the equations, take of the 3 equations you start with, take them 2 at a time and eliminate the same variable 2 different ways. So like pick the first and the second and the first and the third and decide you're going to get rid of y, for example. It doesn't have to be x. You could eliminate x or y or z. It's kind of up to you, but pick pick a variable and get rid of it 2 different ways using 2 different pairs of equations. After you do that, the result will be 2 equations with 2 variables, and then you just repeat the process to get rid of one of the variables that's left. After you know a value for one of them, go back to one with just 2 variables. After you find the second one, go back to the beginning, cycle back around, and you can find the solution for all 3 variables. So that is the end of section 2.